The topic of this lesson is called the rank-nullity theorem. I need to define a few things, in particular, what is this word nullity? So here's the context. So suppose AX equals 0. When you see something like this, what do you think of?
Homogeneous.
Exactly. Is a homogeneous system of equations, of linear equations. And I'm going to refer you to something we said when we started to discuss subspaces, that the solutions of a homogeneous system form a subspace. And the reason for that was that the 0 vector is always a solution, obviously. And that in general, if you take two solutions to a homogeneous system and add them, you're going to get a solution. And if you take a solution and multiply it by a scalar, you get a solution. Okay? So the set of solutions, which is a subset of vectors, satisfies the three criteria that suffice for it to be a subspace. Okay? So let's write that. As we have mentioned before, the solutions to AX equals 0 form a subspace. A subspace of what?
The matrices.
No, the solutions are vectors. In fact, written like this, usually we think of them as column vectors. And how many entries do they have? We called it n, right? It's the number of unknowns in this system. Okay, so they form a subspace of, let's say, Rn, unless the system is over C, in which case it would be Cn. Okay, let's write this. Or Fn for a general field F, where n is the number of variables or unknowns. The number of xi's. Good? Okay. So this, since it's a subspace, it's a vector space, and it's called the null space of A. Okay? So definition, the null space of a matrix A is the set of solutions of the homogeneous system of equations for which A is the coefficient matrix. Okay? So it's a property of a matrix. The null space of a matrix is precisely those vectors which A sends to 0 by multiplication. Okay? And this is going to make a bit more sense when we reach our, well, it's not our next topic, it's two topics in the future of linear transformations. Okay? But we'll get there. So the null space of a matrix is all those vectors that solve the homogeneous system for which A is the coefficient matrix. Okay? So that's the null space. And the first theorem that I want to write is the following. Let AX equals 0 be a homogeneous system with n variables, n unknowns. Then the dimension of the null space, the dimension of the set of solutions, okay, is n minus the rank of A. Okay, the dimension of the null space, which is the same as the dimension of the set of solutions, is n minus the rank of A. Okay, let's prove this. By the way, does this number ring a bell? When you see n minus r of A, this number did show up previously when we talked about systems. Do you recall what it was? Okay, this was right. This was the number of degrees of freedom that we had in the general solution. Okay, so this was the number of variables for which we can choose any value that we want, and then the other variables were already fixed by those values that we chose. Okay, this was the degree of freedom. Remember that? Okay. So let's prove this theorem. Proof. So denote, let's give this number a name, let's call it k. So k is going to be n minus the rank of A. Okay. K is the number of degree of freedom. What we call the degrees of freedom. How many variables can we choose without any restrictions? Okay, and so there are k of the n variables, of the unknowns. So there are k x i's which we can choose. Okay? So we don't know that they're the first ones. We don't know that they're in fact x1 through xk. Maybe they're x2, x17, x135, and so on. But let's write them as the first ones. We can always rearrange the numbering on the variables in order to make the ones that are the degrees, that represent the degrees of freedom, that we can put them first. Okay, so can you live with that kind of restrictive move? Okay, but do you agree that it doesn't restrict anything, in fact? It's just a relabeling, okay? So assume, just for simplicity, I can write everything with the xi's kind of scattered along, but it's easier to write when they're the first ones. Assume for simplicity, that they are x1, x2 through xk. Okay? So these are the degrees of freedom. We can choose them randomly, okay, whatever we want, arbitrarily, but then the rest are fixed. Okay? All the rest, xk plus 1, is some linear combinations of the first one, the first xk ones. And xk plus 2 is some linear combination of these. And xk plus 3 is some linear combination of those. Good? Okay. So a solution, why did I write an H? A solution looks like this. There's x1, x2, all the way up to xk. I'm writing it as a column vector because that's how we're used to thinking of x. And then there are xk plus 1 through xn, which are linear combinations of these. So xk plus 1 maybe is something of the form alpha 1 x1 plus alpha 2 x2 plus dot 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 plus alpha k x k. That's the k plus first entry in the solution. Okay? And then the k plus 2 entry is going to be some, well, I can't call them alphas, I can start putting double indices, but that would be confusing. Let's just call it beta. Beta 1 x1 plus beta 2 x2 plus dot 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 plus beta k xk. And so on, right, all the way up to xn. And xn is still going to be a linear combination of these. So I have to choose a letter. Let's call it, I don't know, c1 x1 plus, I love this letter, it's beautiful, plus c2 x2 plus dot 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 c3 x3. Okay? And so there's an assumption here that there aren't 17 million of these, otherwise I would run out of Greek letters in between, but then I'd throw in what? Hebrew letters, Arab letters, Chinese letters, whatever. Okay? So this is what a solution vector looks like. Do you agree? Do you agree?
Why is it up to C3, X3?
Because ridiculously that's what I wrote. Of course it's CK, XK. Thank you very much. Okay? So do you agree that this is a general solution? Okay. Do you agree that we can rewrite it? We can rewrite it as x1 times 1, 0, dot, 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 0, and then alpha 1, beta 1, dot, 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 c1, plus x2 times 0, 1, 0, dot, 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 0, and then alpha 2, beta 2, dot, 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 c2, plus dot, 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 plus xk 0, dot, 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 0, 1, and then alpha k, beta k, dot, 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 ck. Do you agree? Good? So a solution to the system of equations, which has n minus ra degrees of freedom, looks precisely like this, which is precisely like this. Let's give these guys now new names. Let's call them w's. So let's call this one we're going to call w1, and this one we're going to call w2, dot, 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 and this one we're going to call wk. Okay, they're just names for these specific vectors. So do you agree that w1, w2, all the way up to wk, any solution is a linear combination of these guys, right? Any solution in general looks like this, with some values of alphas and betas. So any solution is a linear combination of these guys. Do you agree? Okay. So they span the set of solutions. Do you agree? Okay. And span the set of solutions, and do you agree that they're linearly independent?
Yes, because of the ones.
Right. Because if ignore the coordinates after the zeros and ones, look just at the first k components of these vectors, they're already, if you set them up as rows of a bigger matrix, they're already the reduced echelon form. Okay? Do you see that? So if you take these vectors, straighten them out as rows of a giant matrix, it's already in echelon. Well, the first n are in echelon form. Okay, so the entire matrix is in echelon form. Once you throw these in, you don't know that they're in Yeah, you can maybe still do some stuff. Do you agree? Okay. So span the set of solutions and are linearly independent because of the first k components, entries. Do you agree? So in fact, this is a basis. This is a basis for the set of solutions, right? So this set spans the set of solution and is linearly independent, hence a basis. So we found a basis for the set of solutions that has how many vectors? K. There are precisely k guys here that are a basis for the set of solutions. Okay? So the set of solutions which we call the null set right? That was the definition of a null set, the set of solutions of the homogeneous system of equations for which A is the coefficient matrix, has a basis with k vectors, and therefore has dimension k. Okay? And that's it. That completes the proof. Let's look back at the original theorem. Okay? The original theorem said, take a homogeneous system of equations, then the dimension of the null space is n minus Ra, which we called k. Good? Okay. So here's a corollary of this theorem. Corollary. And surprise, surprise, I remember, because it was just a few minutes ago, how to spell corollary. So the corollary is ax equals 0, let ax equals 0 be a homogeneous system. With n variables, etc. Then n, which is the number of variables, equals the rank of A, right? The rank of A plus, now I could write here something very stupid, plus n minus R of A. That would be obviously an equality. But what is n minus R of A? It's the dimension of the null space. Okay, so let's write it where this is the rank of A. Another way of saying it is the equals the dimension of the row space of A, right? We know that these are the same. And this is the dimension of the null space, which is sometimes denoted by null A. Okay? So if you want to read this, and this is the number of variables. So for a homogeneous system, the number of variables equals the rank plus the dimension of the null space. Okay? And this follows from, I don't need to prove anything, we just proved it, right? What required proof was the fact that this is the dimension of the null space, and that was the theorem. Okay? So this statement is called the rank-nullity theorem. Okay? That was the title of this. This is called the rank-nullity theorem. Good? Okay. I want to write down a few things that follow from this. Okay? And they're going to seem like a bit unrelated, and why am I throwing this in here? Well, the reason is that they're direct corollaries of this theorem that we phrased as a corollary. But we're going to see their importance in things we do later. Okay? They're really very simple tools, but you have to prove them once. Okay? So there are statements that you're going to say, of course, but everything that is, of course, still requires proof at some point or other. Right? So here's the statements. So let's call it a theorem, and let's have two parts. One is going to say, if AV equals 0, for every V in F n, okay, so let A be, what do we need? We need A to have n columns. So let A m by n be a matrix in M. Oh, I'm writing it in an ugly way. Let A be a matrix in the matrices of size m by n over some field F. Good. If AV equals 0 for every V in Fn, then A is 0. The only system, a different way of saying this is, the only system of equations for which any vector is a solution is the system of equations where all the coefficients are 0. Okay? And the second part is, if AV equals BV. Oh, now we have two matrices. So let A and B. Sorry, let A and B belong to m by n over F. If AB equals 0, sorry, if AV equals BV for every V, then A equals B. So let's prove this. So proof. And the really useful thing is part 2. If you have two matrices and you want to show that they're the same, and this is in theory, in the abstract world, if you have two matrices that are concrete and you see the entries, if you want to show that they're the same, you have to check that every corresponding entries are the same, right? But suppose you have two matrices that showed up in some theorem or in some context that you don't know the concrete entries, Okay, you just know that A, for example, solves some equation, and B, for example, comes from some subspace, or I don't know what. Okay, they're abstract. A good way of checking if they're the same matrix, or a useful way that is sometimes useful, is to check if AV equals BV for every V. Okay, and again, this is going to make a lot more sense when we talk about linear transformations. Okay. So I'm hinting at things that are going to come later, but when they do come later, they're going to sound familiar. Okay? So let's prove 1. And then 2, 1. So what does it mean that AV equals 0 for every V? It means that if every V is a solution to the homogeneous system of equations, AX equals 0. Right? That's what it means that AV equals 0 for every V. It means that every V is a solution to AX equals 0. Do you agree? So this is the data here. If this, then if every V is a solution, the space of all solutions is all of Fn, right? So what is the dimension of the set of solutions? N. Yeah, it's true, N. Okay, then, but how did we call the set of solutions of a homogeneous system of equation? The null space. Then, the dimension of the null space of A is N, right? Because every vector is a solution, therefore the solution set is all of Fn, right? And the dimension of Fn is N. And the set of solutions, by definition, is the null space, right? Good, everybody? Okay. And by the rank-nullity theorem, let's look at it again. It's over here. The dimension of the null space is N minus R of A, right? And that equals N equals R of A plus this. But if this is to be satisfied, and this is N, what must R of A be? 0. Do you agree? There's no choice. There can't be anything in R of A. Do you agree? Okay. So the dimension of the null space of A is N, therefore R of A equals 0. And when does a matrix have rank 0? It means that after we do row operations, all the rows are 0. Do you agree? Okay. So what matrix has rank 0? When can we do row operations and get 0? It's only the 0 matrix. If there was a non-zero row there, okay, somewhere, the rank would be at least 1. Okay, you can't make all the rows die by row operations. Okay? Good? Okay, so this proves this part. What about part 2? I'm starting it here, so it better end very quickly, right? Otherwise, I would have taken a new board already. Well, if AV equals BV for every V, then AV minus BV would be 0. Therefore, A minus BV would equal 0 for every V. Do you agree that from this follows? If AV equals BV, then AV minus BV equals 0. Therefore, A minus BV by associativity equals 0. for every v. But by part 1, the matrix A minus B satisfies part 1. So by part 1, A minus B is the 0 matrix. And A minus B can be the 0 matrix if and only if A equals B. Good? Okay. So these two results are rather, kind of little technical observations, but we're going to see their usefulness in things that will follow. Okay? So if you have two matrices that when you apply them, and I'm saying apply because I'm already thinking linear transformations, and matrices play a role of linear transformations. So I'm saying apply, but what you should see is multiply them. If you multiply them by every vector, and you get the exact same thing whether you're taking A or B, that's it. They're the same matrix. Okay? Good? Okay. So this wraps up our discussion of our entire discussion, which was pretty lengthy. There was a lot to say about this, about linear independence, spans, bases, and dimensions. Okay, it was a big topic. And what we're going to do next is, well, there are a few kind of small things that we want to discuss, small auxiliary notions, things that usually play a useful role, but they're not a big topic. For example, we're going to discuss determinants. I'm sure you've heard about determinants. And we're going to discuss invertible matrices. Okay, when can a matrix have an inverse, a multiplicative inverse? Take a matrix A. Is there a matrix B such that if you multiply them, you get the identity? Okay, so these are little small issues that we have to clear out of the way. We have to know how to do it because it's going to be useful for things that we do. And then we're going to reach the second big topic of the course. The first one was vector spaces, and the next one would be operations on between vector spaces, which are called linear transformations. So that's where we're heading, but we're stopping this one now.